In the realm of 3D graphics, creating realistic and visually appealing imagery goes beyond simply constructing geometric shapes. It's about simulating how light interacts with these virtual objects. And this is where shading comes into play. Shading breathes life into 3D models, transforming them from flat, lifeless forms into captivating representations that mimic the appearance of objects in the real world. Imagine a simple sphere displayed on your computer screen. Without shading, it appears as a flat, two-dimensional circle. However, by applying shading algorithms, we can simulate how light rays bounce off its surface, creating the illusion of depth and volume. The result is a sphere that appears convincingly three-dimensional, with highlights, shadows, and subtle variations in color that convey its shape and form. Shading is essential for achieving realism in 3D graphics. It allows us to depict the way different materials interact with light, from the dull finish of clay to the reflective surface of polished metal. By manipulating light and shadow, we can create the illusion of texture, depth, and dimensionality, making virtual objects appear tangible and believable. In essence, shading is the bridge between the digital realm and our visual perception, enabling us to create immersive and visually stunning 3D graphics that captivate the eye and engage the imagination. It's the magic that transforms simple polygons into believable representations of the world around us. Shaders are the workhorses behind the scenes, responsible for dictating how light interacts with surfaces in the virtual world. They are small programs that run on the graphics processing unit, performing complex calculations to determine the color of each pixel on the screen. Different types of shaders offer varying levels of control and flexibility, allowing artists and developers to achieve a wide range of visual effects. Surface shaders, also known as pixel shaders, operate on individual pixels, determining their color based on factors like surface properties, lighting conditions, and camera position. They provide fine-grained control over the appearance of materials, enabling the creation of realistic textures, reflections, and other visual effects. Vertex shaders, on the other hand, operate on individual vertices of a 3D model, manipulating their position, color, and other attributes. They are often used for tasks like transforming the shape of objects, creating animation effects, and displacing vertices to simulate surface details. Geometry shaders take it a step further by working on entire geometric primitives, such as triangles or lines. They have the power to create new geometry on the fly, enabling effects like fur, grass, and other complex structures. Compute shaders offer a more general-purpose programming model, allowing developers to leverage the parallel processing power of the GPU for tasks beyond traditional rendering. They can be used for physics simulations, image processing, and other computationally intensive operations. Each type of shader plays a crucial role in the rendering pipeline, working in concert to create the final image displayed on the screen. By understanding the strengths and limitations of each shader type, artists and developers can choose the right tool for the job, crafting stunning visuals that push the boundaries of realism and creativity. To harness the power of shaders, we need a way to communicate with the GPU and instruct it on how to manipulate pixels and vertices. This is where shader languages come in. These specialized programming languages provide a framework for writing shaders, allowing developers to define the precise calculations and algorithms that determine the appearance of objects in a 3D scene. Among the most popular shader languages are GLSL, HLSL, and CGG. GLSL, or OpenGL Shading Language, is a high-level shading language used primarily with the OpenGL API, a cross-platform graphics library. It offers a C-like syntax and provides a wide range of functions and data types specifically designed for graphics programming. HLSL, or High-Level Shading Language, is Microsoft's counterpart to GLSL, primarily used with the DirectX API, a graphics library commonly found in Windows-based systems. HLSL also shares similarities with C-like languages and offers a comprehensive set of tools for shader development. CG, or C for graphics, is a language developed by NVIDIA that aims to provide a more platform-agnostic approach to shader programming. It can be used with both OpenGL and DirectX, making it a versatile choice for cross-platform development. While these languages differ in syntax and specific features, they share a common goal to provide a powerful and flexible way to control the rendering process at the shader level. By mastering a shader language, developers gain the ability to create custom shaders, unlocking a world of creative possibilities in 3D graphics.